This session is an update on research in silver at leading institutions of India. The session's moderator is Mr. Srivatsava Ganapathy of Eventell. The panelists that are joining him this afternoon are Dr. Amol Kulkarni of CSIR-National Chemical Laboratory and Professor Nikhil Dhawan of IIT Roorkee. Ladies and gentlemen, please give them a round of applause as I briefly lay out their profiles in front of you. Srivatsava sir is obviously no stranger to this entire ecosystem of metallurgical world and commodities. He is the Chief Executive Officer at Eventell Global Advisory, a premier platform focused on commodities, precious metals, and strategic industry insights. With over 20 years of experience in industry research, event curation, and stakeholder engagement, Mr. Srivatsava Ganapathy has been instrumental in creating dialogue-driven forums that connect key players across the value chain. His leadership continues to shape impactful industry events that drive growth, innovation, and collaboration in silver and broader commodities ecosystem. A big warm welcome to Mr. Srivatsava Ganapathy. Dr. Amol Kulkarni is the Senior Principal Scientist in Chemical Engineering and Process Development at CSIR, National Chemical Laboratory, NCL, Pune. A Senior Principal Scientist doing pioneering work in microreactor engineering and flow chemistry. Dr. Kulkarni has led significant advancements in scalable, efficient, and sustainable chemical processes. His research has earned national and international acclaim, including the prestigious Shanti Swaroop Bhatnagar Prize in 2020, and has bridged the gap between laboratory innovation and industrial application. Please put your hands up for our specialists coming up. Professor Nikhil Dhawan is joining us from IIT Roorkee. A warm welcome, sir. And with this, I leave this session in the hands of Mr. Srivatsava Ganapathy. Please be with us till the end, as towards the end of this session, we will have a one-on-one industry and institution session.
This is a new experiment that we have been doing in the last 2 years. What are the industry doing? Most of us will know. But what the research institutions in India are doing, seldom we come to know. Therefore, we made it a point to extend invitation to leading research institutions in India. So last 2 years we have been having very healthy discussions, and post the conference also several of the industry leaders have gone and visited those institutions and continued the dialogue. So we are continuing the same tradition, but oftentimes what I understood over the last 2 years is that institutions face 1 or 2 challenges. They keep asking, we have the facilities, we have the capabilities, but we don't have clarity on what does the industry want. What are the core challenges which the industry wants it to work on, either exclusive basis or on collaborative basis. Perhaps in this direction, we need to facilitate more one-to-one dialogue is what we took away. So the way we have structured this is that we have 2 eminent professors who have put in a lot of efforts in our sector of interest, and they have developed solutions. First, we will let them speak and share what they have done. After that, if you have some common questions based on their presentations, you can take it up here. If what they do is of interest to you and you want to engage in a conversation with them on a one-to-one basis, post this session, we will request them to be available for individual consultations. This is how we plan to do this one. So with this introduction, I will invite Dr. Amol Kulkarni first to make his presentation.
Good evening, everybody. First of all, I thank Mr. Srivatsava Ganapathy for inviting me here to give this presentation about what we do in our labs. It is certainly slightly different than what you people do, and probably more you know in terms of the real applications than what idea we have. Because you work with the real markets, you work with the real applications. So the real problems and the solutions, you are quite close to those. We are just a bridge to basically connect and understand it from the fundamentals. What I'm going to do is that I'm going to give a presentation on conducting inks. I'm sure that many of you probably are aware about what these inks are because we've used them left and right, but probably we don't know that they exist in most of the applications that we use. So what I'm going to talk about is give some introduction to conducting inks, application, the market value analysis at this point of time, who are the major suppliers of conductive inks all over the world. Then I will touch upon the work that we are doing at NCL Pune, where I will touch upon the silver nanowires and the conductive inks using silver nanowires. Silver on silica, something new because everybody wants to reduce the amount of silver on in any application that you want to do. What you want is a point-to-point contact that must happen, but with as less silica as possible. Then I will go for platinum on carbon, something new, which is probably disconnected from here, but I see that many of the participants here have the interest in the other noble metals also. And then I have something to tell about the electronic chemicals, which again falls in the same category. Thank you very much. So here, what are conducting inks? So conducting inks are basically printable material which contain basically conductive particles like silver, copper, carbon, or it can be in any different form, allow an electric current to flow through it, creating circuits and other conducting pathways on various surfaces. Now these surfaces need not be flat, these surfaces can be curved, these surfaces can be flexible, these surfaces can be kind of printed. So there are now the electronics is completely getting printed along with the conducting elements into that. Now that is where you need something like conducting inks. There are three different compositions of, major compositions of conducting inks. First is conducting material, without which it will not become conducting, that provides the electric conductivity. Second is a binder or a polymer that holds everything together as a matrix. In general, these binders and polymers, if they are also conducting, it helps a lot. Third is the solvents and additives that allow you to mix these materials together and make it kind of a formulation or a paste that you can kind of apply or print on any particular surface. There are three types of conducting inks. First is the metal-based conducting inks that use finely ground dispersed metal nanoparticles, metal microparticles, and other shapes which basically are mixed having high electric conductivity. These are primarily three types: silver inks, copper inks, and the gold inks, having applications in specific areas. Then comes the carbon-based conducting inks, mainly the graphene and graphene oxide. So these inks use basically carbon nanomaterials, and the main problem there is the color. You can't get away from the gray color or the blackish color from these materials. They offer high flexibility, they are lightweight, and in many applications, graphene inks are preferred as compared to the metal inks. The third is conducting polymer inks. Now this is something kind of coming very fast. There are a lot of Chinese companies who are working in this domain, and a lot of new organic polymers are being designed and synthesized, which are all conducting polymers. So it uses organic conducting polymers instead of metals or carbon materials. They are flexible, they are lightweight because they are polymers, and they can be transparent. So it depends on the property of the polymer. And there are different types, and there are few companies who make those ingredients in India, but they don't use it in the end application. So we supply all of these polymers to foreign companies. What are the advantages? They are flexible and lightweight, all the conducting inks. They are cost effective as compared to using a metal to make a printed circuit board. They are easy to apply because you can print it on any surface, and it's a scalable production. So it's like any other chemical. As compared to the traditional techniques which need etching, soldering, sometimes you need lithography, kind of a very highly intensive unit operation. Making conducting inks and printing them is relatively cheaper and far more disintegrated. So you can kind of take it anywhere you want to actually do the printing. There are different features of comparison of these two printing techniques. I will share the slides with the organizers so that they can share it with you. There are a couple of excellent advantages. The first is, as compared to any other conventional process which needs multiple unit operations, right from the cleaning the surfaces, etching the surfaces, lithography, bonding, soldering and all, your conducting printing doesn't need all these things. What you need is absolutely clean surface, and that's it. More importantly, there is a huge variation in terms of the material that can be used. So silver, copper, graphene, CNTs, PDOT, PSS, there are many polymers. All of these together make these conducting inks, as compared to always you need copper clad boards or silicon wafers or etching materials in the other. So there are a lot of advantages of the conducting inks as compared to the conventional techniques. And where do all these inks go? When I say inks, they are all printed. So electronics industry, automobile industry, consumer electronics, medical and healthcare, like printing your ECG electrodes on the go, wherever required, whenever required, printing and packaging, energy sector, and aerospace and defense, because what you want is a lightweight materials in those segments. And application-wise, there are a lot of areas where you find many applications. The most common thing in all these applications, you need silver. Without silver, you cannot make a conducting ink as such. There are efforts are being made to replace silver by copper or reduce the quantity of silver by using enhancing the quantity of copper and so on. But you cannot get rid of that. So what is the market value as of now? Conducting inks market is $3 billion in 2020. It's expected to be to 3.9 billion in this financial year. More importantly, the CAGR is basically 8.2, which is a good driver for anybody to get into this domain. There are primarily 4 aspects. It's increasing demand and efficiency and miniaturization of the devices. Everybody wants compact devices. Everybody wants slick mobile phones, foldable mobile phones and all. So that is where the conducting inks become far better, because what you want is something which is flexible. Restraint, the requirement of high-end technology, that's a constraint at this point of time. But with the availability of different types of printers, it is very easy. Third is an opportunity, development of cheaper alternatives to silver-based conducting inks, which means that there is a possibility that you can reduce the content of silver and increase the content of the polymer which is conducting and the copper. What are the challenges? High cost of silver-based conducting inks, because you need to compete with the known materials. And by type of silver conducting inks, the segment is projected to account for the largest share in the time to come. I have one case at the end I will show, where the RFID market is the biggest one. These are all the companies which globally supply silver nanoparticles based conducting inks. Fuji is one of the largest, and they have multiple manufacturing and formulation plants in India. And these are all the applications where it goes. You don't find a single Indian company here. We are way behind in that entire domain. As I told, RFID market, the largest one, because as the number of malls increase, as the population is increasing, as we are buying a lot of things from the malls, we need RFID tags almost everywhere. So the RFIDs you need, and everywhere you can't do the conventional printing. You need to have a conducting inks getting printed there. So RFID is going to be the largest consumer of the silver-based conducting inks. There are companies who supply silver nanowires-based conducting inks. And these are all the major players, which are almost 7 major players, all out of India, and there is only one South Korean company. Interestingly, the first 2 have recently been taken over by a Taiwanese company. So that becomes number 1 at this point of time. And these are the companies who are basically supplying the inks for our touchscreen. All touchscreens, wherever we are not using the ITOs, that is where these formulations go. Whether it's your iPhone or any foldable phone and so on, it's all based on the silver-based conducting inks. Alternative, copper nanowire-based conducting inks. This is gathering the speed, but there are few challenges. Copper gets oxidized very fast. So you cannot have copper alone. So what people do is that they coat silver on copper. When you make the copper nanowires, you basically give a very thin layer of silver on that, and that makes it stable. And it reduces, while there is no compromise on conductivity, it reduces your overall cost. So there are copper nanowires and copper nanoparticle based conductive inks. And in India, we import a huge amount of conducting as such. I feel that as we are getting into chip manufacturing of the chips, assembly of the mobile phones, assembly of the electric vehicles and so on, I think our requirements of the silver-based conducting inks is going to shoot very soon. And we will not be able to afford completely importing it during this tariff war. So we have to have our own inks being produced in India. So let me I will show you some of these things which are happening all over the world. Because everywhere if you see, there is either a copper or copper nanowires or a silver-based ink which is being, so people are exploring how do you make it better and better every time. Now let me come to why some work that we do at NCL. Now why silver nanowires? I have been coming to this forum for last 2 years. I have been talking about it. There are very specific reasons. Wires are very long as compared to the particles. If I have to coat a surface with the particles or a paste or anything, I must need to have multiple layers to make sure that the particles touch each other, because if there is any gap, I will not be able to do any charge transfer. But if I have a wires or network of wires, it is more like the wires that can touch each other even at 1 or 2 points, and that's enough for me to do the charge transfer. So it's highly thermal and electrical conductivity. It's a low sheet resistance. As you reduce the size or the diameter of the wire, it becomes transparent. So iPhone touchscreen is transparent because the wires are thin. And it gives a large open surface area. The cost point of view, it is really expensive at this point of time. There are many applications of silver nanowires, and this is how they look when you actually synthesize them. They are like the wires. It's a thick kind of a crowd of these wires which are crossing each other, and you can just make a solution, a very thin solution out of this and make it. So there are challenges when you make silver nanowires. It is not very straightforward, like you are drawing it from a silver bar or something. It starts with a silver solution. And so what you need is silver nitrate, which has to be used as a solution. It's like a chemical method that gives you eventually the wires. There are a lot of complexities involved in it. Now we have optimized this process. And more importantly, depending on what is the rate at which you do this synthesis, you either get thin wires or you get these kind of rods that you see at the bottom. Now, any guess about what can be the shape of these wires? Anybody? What if I cut this wire? If I cut this wire in 2 pieces, what will be the cross section? Okay, these are pentagonal wires, very unique shape. You cannot make circular, like carbon nanotubes are get a circular cross section, but silver is always a pentagonal wire. So that's because of the crystal. The crystal does not grow in a kind of, you can have a spherical particle, but as the wire starts growing, it becomes pentagonal, and that pentagonal rod continues to grow as it grows. And eventually, so far your particles have this pentagonal cross section, you will always get the wire. If it does not have pentagonal cross section, you will never get a wire. So how do you kind of control that condition? That is the skill. So we have worked on this. We make these wires in significantly good quantity. I have a video here. I do not know if it works. No, it did not. We have formulated the inks based on what you see here, the horizontal rods. Actually, it's a video. How do you make those inks? So just it's a 1 minute video. Yeah, so you mix. So you basically take the nanowires, you add a solvent, which is IPA plus acetone plus 1 binder. So you take a thin slide, glass slide, you coat it with this material. You allow it to dry for some time, and when you dry it, after drying, you see if it's conducting. So you can see that it is transparent. So we have put it on a colored diary. You can see that the wires are connected from 2 points and the LED is lit. So basically we can even kind of make a paste out of this, or you can do the screen printing, apply this paste made out of silver wires, then you kind of spread it on the screen. Then whatever the pattern that is formed there, you basically dry that pattern. So you will be able to see here, it's a thin circuit that we have formed. You keep it at 60 degrees centigrade. Now this 60 degrees is enough for the wires to sinter. They are nanometers, so you don't need to go to a high temperature. So it's 60 degrees centigrade, it sinters. Now you see it's printed on paper. You are able to kind of lit a bulb. You can also see, you can make a glass is made conducting. The moment you put a multimeter, you can see that the color is changing. Second important, it also makes it triboelectric. So if I press anywhere, it uses that pressure energy into electric energy, and so you can see that the voltage gets applied. So a lot of things can be done with the help of these silver wires. And so all your pressure transmitters, your ECG electrodes and all can be made based on these inks as on when you need. So let me go to the next slide. So what you get is a thin film with 95%, more than 95% transmittance. You can't see the screen, and still you have the conducting wire. We have something innovative. So what we did for last few years, we have now improved this process of making these wires. Earlier it used to take kind of, in the lab we used to make 500 gram wires every day, and 1 gram costs somewhere like $140. So in the lab we used to make 500 gram. but it used to take little longer time in terms of reaction time. Now we have reduced it, the reaction time to 5 minutes. And 5 minutes we are able to kind of make a good quantity of the wires in a very short time, in a very short reactor that we have. The entire setup will sit on half of the table that is in front of you, and that allows you to make wires which are with 98% conversion, more than 86.6% yield. Nobody has ever been able to achieve this kind of a thing. And you can see it's like a crowded nanowires film. You can kind of take it, make inks out of that and make the conducting inks. And this is the economics. So if you see, these are all the materials which we have used. This is the total raw material cost for making 100. This is what is the market price, $80 to $140 per gram. This is what we make, $8.7 per gram. So it's a huge difference in terms of the price. Similar thing goes if everybody wants to reduce the amount of silver on any substrate, any application. So we are working on that. How do you kind of coat silver on carbon, silver on silica, silver on anything which is ceramic and so on, because that reduces your silver coating. What you want is a contact conductivity. So we have been working on how do you, there are a lot of applications of this, because as the thickness of silver on silica changes, your application domain changes completely from automobile to the electronics to the EMI shielding. So we have been working on this. We have made kind of different levels of coating using silver on silica. You can see right from very thin particles coating the silica to a thick patches, and in all these cases the amount of silver that has gone is negligible as compared to if I need to use this entire silver particle. So that reduces your, the last couple of slides, this is one I wanted to show. I had shown it last time also, because now we have a lot of improvement in it. The platinum on carbon is a very, very important catalyst, not for the hydrogenation reactions in the industry, but in the fuel cell, in all your automobile electric vehicles in the time to come. The general thing is that you need 40% platinum on carbon, which is unheard of, which is very high quantity. There are very few companies all over the world who are able to make this and produce it. So we started working on it because there is a huge market. You can see by 2030, it's close to almost $1.4 billion. That's the market. You can see the prices at this moment per gram. So if you see per gram, it's $192. That's what the fuel cell store sells it. The other 60% platinum on carbon, 5 grams is available at $1,170. It's a high value material. So we started working on it. Now there is something interesting. In all these cases, for this particular catalyst, your particle size has to be between 2.5 nanometers to 2.7 nanometers. If it is more than that or less than that, it doesn't give the application. So we have been able to now fine tune that thing, and we have been able to get excellent dispersion on the carbon surface. And as compared to the most kind of sold platinum on carbon catalyst for fuel cell application, this Johnson Matthey, we have been able to compare. You can see our application. You will not be able to differentiate between what JM catalyst gives and what our catalyst gives. We have been able to match the performance almost perfectly. Last slide. So in the last week, there is something came out on silver nanowires. So DuPont announced it in South Korean automobile exhibition. So DuPont announced a silver nanowire-based conducting ink in the automobile sector in South Korea, where it's mainly for the electric vehicles and autonomous driving. So what they are doing, they have multiple transparent heaters in the car. They have got cameras, headlamps, everywhere coated with silver nanowire-based inks. These are smart surfaces. If I see that outside there's a lot of light and I'm reading something sitting backside and I don't want to have so much of illumination, I can just tap on the glass and it will basically make the glass slightly hazy. This all because you are having a coating of conducting ink where you are able to change the basically transparency depending on the voltage that you pass through that. So it is possible to play with this, and so by doing that, you are able to have so many variations in a single car. It has advanced driver assistance systems, electromagnetic EMI shielding so that your load on the AC in the car decreases, and it's an infrared reflection. So there are a lot of important things which are happening. This market is going to thrive. If India is going to be the largest consumer of the electric vehicles in the time to come, I think we need to have our own inks. We need to have we should be able to supply with pride to Tata Motors, Mahindra and so on, because they are not going to reinvent those things. It's all the silver community who has to do that. Thank you very much for giving me an opportunity.
Thank you, Professor. That was indeed a lot of work. I'm sure we will have many questions. Let's wait for the other presentation by Professor Nikhil. He would speak about what their institute, which is IIT Roorkee, which has done when it comes to recovery of precious metals from electronic waste. Over to you, Professor.
Good evening all. It's an absolute pleasure to be in front of such a pristine audience working on silver and gold. Very much thankful to the organizers for inviting us and showcasing what we are doing at IIT Roorkee. So I am Nikhil Dhawan. I am one of the among the three listed here. So we come from institute which has 175 years and more than of existence. Probably the oldest and the first in Asia. So this was our history, started in 1847 by Britishers. Now we are at 2025. So moving on, so I want to show you a metal wheel, because from morning we are listening silver, gold, silver, gold. I thought let's to put in a prospect that because somebody will say we want to mine, some will say we want to extract, somebody will say we want to use as a customer also. So in short, this wheel shows you very clearly that whatever you do, silver and gold cannot exist on their own. They will always come with lead, zinc, copper. Number one message. Number two message is, since they are always used as an alloy, or they will be used as a contact, so you expect them to come up along with some other metals, mainly copper. Now, to understand it furthermore in context of recycling, if we talk about let's say tin, which comes as a majority in a solder material, if there is copper, tin, gold, tin says, I am sorry, you cannot extract gold, because tin will make you a big trouble for copper also. And if copper is a troublesome, gold cannot come. It's like a short story. In a jungle, if a lion hunts, hyena is the one which will hunt away all material from lion, some fraction. Similarly, in electronic waste recycling, copper is the one which will take gold with its own, but tin will be the one which will stay there. So these metal associations are very important to understand if we want to recycle them to the level that we really want to extract out. So in short, we are kind of enclosed in such a circle where lead, zinc, copper, nickel, these major four base metals will definitely affect how silver and gold will be extracted from electronic waste. So in short, these products, what we are trying to extract gold and silver from them, they are very complex because they are made that way, number one. Because these products are not made for recyclability, but these are made for working performance. So the era has come that you have to design the product in such a way that it should be recyclable. Otherwise, it has to go into landfill. Now, the metal wheel last message is that no part can exist on its own. So starting from production, application, recyclability, they are highly aligned with each other. So first time we'll be talk about printed circuit boards. We are talking of a number of 62 million metric ton per year globally, out of which say 50% comes from Asia, and please mind it, only 20% or even lesser than that is formally recycled. Rest all is very lucky to go to Europe for being recycled. The previous speaker mentioned about Umicore. The major chunk goes to that. Then among India, we are talking about of roughly a volume 3 million metric ton per year, this number. Now what 1 ton of printed circuit board can offer you, it can offer close to 100 grams of gold, provided the process is correct. It can offer you palladium, silver, nickel, etc. and many more, and the economic value itself is quite high. But gold is always positioned in such a way that it's on a contact material. You can never get it gold as a free, just like it does not exist in nature also. And the major market share comes from gold, only 65% of the total value comes from gold. The challenge is how to find gold. So if we compare primary ores, what we are talking about versus the PCBs, These are at least 10x more than what ores can offer you. And if we look at cost of metals also, one message has to be there that, please mind it, gold and silver alone cannot contribute to complete economical recycling. Other metals has to sustain with that. Then only it will make sense in such scenario, because the cost of tantalum itself is also 1/3 of silver as of today. So it may also boom up. Now if we look on the gold demand and silver demand, so for your, let's say brevity, the technology 7% and 80%, so 6% is directly going into from electronics. In silver demand, this number is close to 25%. So that means we are tackling such a small volume, but provided there is no option, otherwise it will go in landfill. There is no other option for us. So this is what globally industrial processes are doing. They are very good at that refining, which is being exactly copied from what primary ores were doing. And in India, refining is not done to that extent, primarily because the labor is cheap. It is better to do sorting, and the foreign players will take the cheesecake out of that. So moving on, this I told you, since gold will be like a sticking part for copper, so copper will take along all with that. But unfortunately, IIT Roorkee does not agree, but what is being followed for so many years, we said our approach is different, because we know we have spent plenty of time on reverse engineering. What component is what, and where these metals are positioned, how they are associated, how they should be delinked. Now this is the catch, because some companies who will make contacts for electronic industries, they will never reveal you where it is going exactly. And there is no way you can find out the guidelines exactly where it will end and how it will come back. So that means there is a bottleneck in each step, from producer to a user and to the end point, and at the end of the day it will go just to a landfill. So this is a small video if you can play. Yeah. So on this video, the process looks very simple, yes, because this is how we started, and where we are ending is, we are taking this concept to AI, ML, robotic arm, because we know the composition of each of the component now. The yellow ones contain tantalum and silver, the ICs contain silver and palladium, and so on other capacitors. So once this is being programmed from hundreds of boards of characterization, with that knowledge, we can put a robotic arm, we can separate them and put it on a separate process. So this is the driving force. So the boards will look like this. So the highlighted ones are the one on which gold is present and silver. So these are the devices which we should look for recycling of electronic waste. So it starts with integrated circuits, capacitors, tantalum capacitors, Mylar sheets, ball grid arrays, random accessory memories, chip cards, and these are the silver and gold percentages in them. This is the blueprint number on that, and these are their different applications. And gold is always present irrespective of wherever it is going, in few micron thickness, very few, roughly order of 2 micron or so. First case is what we looked at is end of life RAM connectors. Can we extract gold out of them? RAM is being used to fasten the speed of your computers. So we looked at it, gold is of order of somewhere around 2%, 3% at beginning, and gold is always microalloyed with copper, nickel, iron, cobalt, etc. The thickness is close to 2 micron, rest is copper. So we have the methodology, recipe for this, that we can selectively remove copper and nickel, because gold being noble, it cannot go out. So you do the reverse engineering for that, and you opt, instead of nitric acid, you go for an organic acid like MSA. The cost is more, but benefits are far better. We look at the underlying chemistry, how we can dissolve them very selectively. So based on this, you develop a process. There are two ways. One is first you do leaching, then do you do pyrolysis, because since there are plastics also 30% by weight into that, you need to take care of plastics also for a sustainable fuel. And then we look at the performance, everything dissolves appreciably well. Based on this, if we do pyrolysis, if we try to tackle plastic first before the metal, you will always end up in metal loss. Gold will be lost into that. So we could see gold, only 4% can be extracted. So this does not work at all. And the science behind that is that because polymers on being burning, they break into very small particles, then they adsorb onto the surface of metal. So this does not allow the solution to diffuse through, and gold will not be leached away. So it's very good way in the sense that we take the gold fingers out, in which gold is present in micron thickness. Rest we take copper and glass fiber also out of that. And finally, we can get a solid gold product. This is a local jeweler report purity and the carat value out of that, and patent is applied for us. For details we can discuss. The previous speaker very nicely presented about solar panels, so I just thought to bring it. So we are talking about of the concentration of 10 to 600 milligrams per kilogram. This number ranges a lot because these solar panels which were collected 5 years back, they have higher silver values. The ones which are collected now, they have extremely low silver values. So in short, being a teacher, the principle is you compare solar panel to a sandwich or a burger. The biggest chunk is in between, that is silver. So you have to take away the layers from top, layers from the bottom. If you are able to do that, you get the product at home. And this is what we get it. So this is a patent applied, an application for us. We can discuss further details with you. These can offer silver and solar cells after you. Please mind, these solar cells cannot be put back into the solar panel manufacturing because the purity of the dopants, etc. will also change. It will not go in the same direction. Third is what very good source, multi-layered ceramic capacitors. These capacitors look like at the top, and they contain silver as well as palladium, appreciable. So thing is, if you ask to sort out them from printed circuit boards beforehand, this is a highly enriched resource for you. And the structure of that is a standard structure of any capacitor in which there is a dielectric layer. So we looked at this, we have a recipe for it, patent applied for us. So we can discuss details for you. It can offer you, so right now we can offer you a product of palladium hexachloropalladate, one salt instead of a metal, and then silver as an Ag2S or a silver in the AgCl form. The next is tantalum. It is out of silver conference, but yes, silver is also present as a layer. So I thought to put in. So silver is present on a very thin streak layer into this. So if we can develop, we have a process for it, we can take out silver, which will come with silver and manganese and silver chloride, and tantalum will be the one which will cost to the process, and it can make economical process. So it goes very well. And finally, we have a flow sheet where we can show you that we can recover tantalum 100%, and tantalum will cost 3 times more value to the silver if it is being recovered both. Single silver cannot add to the economic process. Yes, this is a keyboard. Nobody would say it has a silver. Yes, it has a silver. So these are called mylar sheets at back. So there are two, one is black, one is silver. So we checked that thoroughly, and our message is all mylar sheets should not be recycled, only silver ones, not the black ones, because black is polymer sheet rich only. So you can, based on this, we have a process on the right hand side. We can offer you only silver, we can offer you silver with 100% polymer recovery, which can be re-put back into any polymer bottle recycling facility. So that can offer you 2 products. And yes, if we do pyrolysis, we can see silver streaks in the third photograph, but they will be embedded again because polymer small micromolecules will take these precious metals into their pores and never allow to release out. And finally, we get the silver ball from such mylar sheets. You will say only 1.24 gram because the weight of sheet is hardly 2.4 grams. So if you scale up, the process is readily available for all scale-up industries because these are standard unit operations pyrolysis available. Last is integrated circuits. Still we are working. These are in plenty used in all communication devices also. And silver is embedded into small fraction. So we look at microscopically in detail where they are present, and based on that we develop a recipe, because polymer has to be removed first, then you get access to metal for its final recovery. So we can recover different metals, we can recover silica based also. And what we are currently doing is, there are special kind of, we call CPU in a CPU. So there is a small CPU on your central processing units in which these ball grid arrays are there, which are source of gold, which are source of silver. This is the only solder in the world which contains silver. Rest all will have tin with it. So we are recovering these solder balls, which will be part of silver contribution to us. And last, we are moving on these processors which are used as heat sink in your systems. Yes, credit card and SIM cards also. They have also gold into that, but a small fraction. But nevertheless, otherwise it will go into the bin because there is no process. And last is these special, what we call single layered ceramic capacitors, in which silver is doped from last 8 years. So this is also coming into the market. For solars I have done. So conclusion, electronic waste is a potential source of precious metals because they are as coating contact connections. Number two, if you have in-depth understanding where these are, because the supplier will not tell you, then you can develop any process for recovery and recycling. Last, a 1 ton PCB can offer you 100 gram of gold and 300 grams of silver. Last, a futuristic approach is to selectively target the recovery. You have to be very focused to get the selective recovery, otherwise you will end up in a complete solution which does not have any solution. That's it. Thank you. I'll be more than happy to answer any question.
First of all, a round of applause for both our professors for sharing what is going on in their institute. Thank you so much for. Slido, can you open it? Like, if you have any generic questions for them on what they have presented, please put your questions here. I'll try to ask them the answers for. I'll start with Professor Nikhil. You said you have patents for some of the technologies, what you have said. What's the general process involved? Like, how do we take it from here if somebody wants to be interested? Like,
So it's like roughly a patent process will cost close to 3 lakhs to 5 lakh rupees. And we give the complete service for installation at lab scale. And then there is a mediator, what we call, who will take up to that required level, up to 500 kilogram, 1 ton per day, based on their request. So we give the process know-how, technical details, and help for all the equipment required for the same. So it's complete technical know-how.
right, this is what you have done already. Like, let's say, like, if the industry is also, if they have done something in this and they have any specific challenges, so do you take it up as a exclusive consulting project?
Yes.
You can do that also.
We generally take a consultancy mode projects. If they are already into it, we can help them in terms of process development or process improvements or yields, the metal yields involved in that.
So what you have patented, you don't have you have a lab scale plan. You don't have a commercialized.
No, it's a lab scale.
Right, thank you. Dr. Amol Kulkarni, same question to you. Like, what's the process involved? How does industry engage with National Chemical Laboratory?
Yeah, we are a CSIR lab, and it's a Council for Scientific and Industrial Research. So we work on the problems which are very close to the industrial relevance. The way we work with the industry is that either we take a problem from the industry to work on and solve the problem and give the solution to the industry, or we develop the technologies or the processes and license those to the industries. In the process, we file few patents, and the process patents are also licensed to the industries. So during this licensing, there are 3 stages. The first is the demonstration. So we give the demonstration of the technology to the company 3 different times so that they check the reproducibility. We hand over the materials to the company so that they can do the testing and come back to us to check if there are any deviations than what we have kind of proposed in the proposals. Second is we hand over a complete technology document for given capacity of production. So that includes like a ready to use document using which anybody can put up a plant. And third is that at the time of commissioning of the plant, we will be there at that point of time, because to help your people to make sure that you are getting what we have promised. That's the way we work.
Is this transfer on an exclusive basis, or you can give licenses to multiple agencies, multiple
Okay,
organizations?
so there are multiple options available. Typically, if a problem has come from the industries, then it becomes an exclusive problem, exclusive thing. There also, there is a rider that if an industry gives us, which typically happens in the chemical industry, not with the metal industry. If somebody approaches us with a particular chemical to be made, manufactured, or a process to be developed, once we work with one company on one molecule, we never repeat that molecule for any other company, because it's not good to kind of create competitors based on somebody else's money. So it's like it becomes more or less exclusive, provided the company starts manufacturing it within 3 years' time, because we are audited by CAG and we have to show that whatever the time that we have spent on it, it has been fructified. There are many experiences where companies give us the project to block the entire area for somebody else, their competitors. So for that, this provision is there. Other than that, if a company, whenever we develop a process based on the Government of India's funding, in general it is non-exclusive unless and until there is a reason that somebody is the largest manufacturer of something on which everything else is dependent, then we have to give it exclusive. So there are kind of a few set parameters using which we license the technology.
Should the company be an Indian company, or you are open to?
Not necessarily, but definitely not a Chinese company. So we have refused many times to the Chinese companies. Yeah.
Right, thank you. Professor Nikhil, one question, I think it is for you. In your projects, have you worked out the economics, or have you worked out the cost, what it is involved? Like,
Yes, we have worked out. We can share the details.
So it is.
It's positive cash flow.
Yeah, because Professor Amol Kulkarni had given a very, very optimistic
Yes,
figure.
we can share.
So it is, in your opinion, like, it is commercially viable and doable project?
Yes, it's commercial.
Sir, all your this technology are pollution compliance? Meet all the pollution norms?
Yes, we take care of those, because because anybody has to, because most of these things are manufactured and anybody has to get the environmental clearance for that. So we have an end-to-end technology. We don't kind of leave anything unanswered or something like that. Yes.
Thank you.
We should appreciate the presentation for the reason is that, earlier research slides will have, a lot of research material. But these research slides are, supported by the commercial numbers. What is the market value? What is the process cost? Means it is so much transparent. Yeah. So actually we should appreciate the kind of quality of the presentation I'm saying.
Thank you. Thank you.
Thank you.
Number two is that how do you decide the technology transfer cost or the license cost? What is the base for that?
Okay, we have a business development group, but what I will tell you the process. What they do is that they ask the company, what are your plans, and what level of market size you want to capture, and they study the growth market rate, how the prices are decreasing. Because prices of these things will continue to go down only. Because to tell you very frankly, when we started working on these mainly silver nanowires in 2017, that time per gram the silver nanowires costing was $150 to $400 per gram. When we announced a process in January 2020, that we have a process which is 12 times cheaper than the price in the market. That immediately after that, within few months, Silver Institute also published it in their annual report. And what we have seen is that within 3 months after that, the prices have gone down by 50%. So it was like the monopoly. They were kind of, and we got so many inquiries from many companies all over the world asking us for the process. We have licensed it to a few, one Indian company on a non-exclusive basis right now. And so as you said rightly, yes, the costing of the licensing is decided based on what is your appetite to manufacture that particular material, what is the growth plan. In general, we are not very, very expensive. Purpose is that whatever the time that we have spent in the lab, it should benefit some company because you will generate more jobs. It's more like an indirect giving back something to the society, because we are a public funded organization, money should go back to people.
Last question, when you had presented some international prices, I was looking at the presentation of nanowire. And when, when it comes to the price for the Indian manufacturer, so they always expect, very drastically reduction in the prices. International prices are not applicable for Indian manufacturer. So with that reference, maybe you have to also give some discounting to the Indian manufacturers.
That is happy to. So it's all about, see, we are a government organization, we are not a profit-making company or so. So kind of anybody approaches us, we'll be happy to discuss everything in detail. And our business development group, the final objective is that the technology developed in the lab should get into the practice in the industry. That's the objective. Thank you.
Yes, Dr. Trevor.
Thanks both, really interesting presentations. I've got a question for you, Nikhil, actually. Traditionally, you mentioned Umicore, their business model was very much originally based around having a certain quantity of gold in their waste streams, because ultimately the gold is what, economically funds the sort of recycling. That has, over recent years, become more complicated as less gold has found its way into some of these devices and some of these circuit boards. So your approach, have you taken all of that into account? Do you need a certain quality of circuit board, for example, to make your... You do. And obviously that's changing all of the time. So how are you kind of dealing with that as an approach?
For, let's say, if you are talking about printed circuit boards, if you just want to put in as a smelting, the gold will be recovered probably at the end, and with some nuisances caused by tin also. And then there is again, ultimately you have to dissolve further and further into aqua regia to get the purest value out of that, because some partitioning will take place for metal in slag and molten metal. But here what we are advocating is that if we know the components in which gold is present, we should tackle them differently, because that process does not require smelting. So that is our dialogue for the same.
Right, so I'm sorry, I missed the very beginning of your presentation, so possibly I missed that, but so you're very, very selectively taking components out.
Yes.
And you're relying on a thorough understanding of where the gold and silver actually reside within the components. Yeah. Okay, I understand. That's really interesting. Thank you.
Yeah.
Thank you.
Thank you.
Yeah, there is a question for Professor Dhawan. I'm not sure, it's the right question for the professor, but he has indirectly answered that. What you buy, be mindful of it, what you're buying, the components in it matter a lot. That's what he mentioned. So is it a challenge? Did you face any challenge while buying this waste?
Yes, e-waste collection is a challenge, because, unless and until there is a buyback policy, nobody is going to throw their electronic waste at required places. So there are companies who are collecting e-waste. They may remunerate for that. Unless it is highly competitive, I feel like from my context family, I will say, we try to keep the things as long as we can. So that habit has to be changed. There should be a buyback policy. Then only the collection will become more. And most importantly, not only collection, it's the heterogeneous nature of the e-waste. In fact, no two boards are same. So that is a challenge involved in that.
For the audience, I would like to let them know, government is encouraging this process, recovery of precious metal failure, and they have declared a lot of subsidies on the investment. So we should take this opportunity. For the production of 109 gram of gold, they are using 1 ton of reserve. 30 gold mines get 5 gram of gold in 1 ton of ore. So it must be very, very economical in my calculation, roughly. And that 30 is costing about $1,500 per ounce. For this much, you calculate how much. So it must be very profitable from the business point of view. And you are getting all the help from the government also. It is a good opportunity for the jewelers and refiners.
Thank you, sir. Any more questions? We have run out of time. If there are any generic questions. Thank you so much to both Dr. Amol Kulkarni from National Chemical Laboratory and Professor Nikhil Dhawan from IIT Roorkee for their excellent presentation. Hope you enjoyed it. Round of applause once again for the professors.